upon a washing machine is they're pretty commonly used everywhere, and I thought it'd be interesting just to go throughout how you might go about making one. So for the specifications, it needs to do what a washing machine needs to do, which is allow the user to select the temperature, the speed, and also the water amount. The temperatures, the spin speed, and the water amount are kind of arbitrary, but they're based on what a typical washing machine would be. So the cold would be 15 degrees C, the hot would be 55. The slow would be 800 RPM, and then the high would be 1600 RPM. That's kind of based off of the more high-end washing machine, so to speak, but I figured since this is a theoretical, it'd be fine. And then the amount of water is based off of the more water efficient washing machines, which in total for the whole thing would be 15 gallons for low and then 30 for high. All those choices that they made wouldn't begin until the user actually confirms that they want to stick with those choices. And as you will see in my diagram, if they choose not to confirm, then it'll reset them so that they could either decide that they actually did want to make those choices or just choose something else. Then after that, everything will be automated. It'll fill up with water, go through all the cycles, fill, wash, rinse, and then spin. And then after it's complete, light will come on and a little chime will go off saying, "Hey, come pick up your clean clothes." So it looks kind of involved. This is just for the selector. It's honestly only this full just because there's so many different choices that the user can make. So I'll just like go throughout how it might occur. So we start off in our little fresh state right here. An LED will be on saying, "Hey, we're in the temp selection state, so feel free to choose the temperature." That would be done through this switch right here. So the clock's pretty slow to allow the user to make their decision. So let's say hypothetically the user selected hot water, which would be, I'm going to say like a sort of toggle switch. So they choose hot. We then go into the hot water. It turns off the temp selection LED, and now we got the spin selection LED on. And also to let the user know that they chose hot water, it'll set on the hot water LED so that they remember the choices that they're making. And then let's say that they choose a slow spin selection speed. We're now into hot, slow. F equals 0 would be, these LEDs would also be connected to flip-flops. One of them would be on Q, the other Q not. So by default, cold water, slow speed, and then also low spin would be all on by default, but you know, they'll be changing it. So now the water amount LED is on, and now they could either choose high or low. In this instance, let's just imagine that they chose high. So now they're in the hot, slow, high. It'll set on the high LED, and after which they could either confirm their choice or decide they don't want that choice. In the event where they said no, it would go all the way back to the fresh state, and it would reset all their choices and turn back on the temp selection LED. But in the instance, let's say that they chose that they liked their choices. It'd go all the way here to this conditional output. This would be asynchronous. And it would turn off my selector machine. And in addition, it would turn on the next part of the machine, which will be fill cycle S2. This would be accomplished through a voltage switch, which will say which machines are on and connected to the clock and which machines are off and not connected to the clock, which allows me to have, it's essentially one machine and there will be different cycles throughout that machine. So right here is the fill cycle. As I said before, it's only active when S2 equals 1. We start right here with begin cycle. And this right here would be controlled through a switch that is dependent on the lid being closed. If it's not closed, it'll do a little chime. It'll say, a little LED will pop up saying, hey, you should close the lid. And it'll keep repeating this until they actually close the lid. After they close the lid, it'll have this conditional output right here. It'll lock the lid, and then it'll also set the fill LED to let the user know that the fill cycle is about to start. So now we're in the temp chooser state. This right here is dependent on what they chose before. So I think in our previous example, we said hot. So let's say they chose hot water. It'd go down here to the fill hot. And then again, this depends on what they said before. I believe we said low before. So it'll go into fill hot low. And now it's going to engage a pump that'll just start pumping in hot water. It'll let in a little water through where the detergent's kept so that it's mixing this in with all the rest of the water. And also the impeller for the washing machine will start spinning very, very, very slowly just to kind of help the detergent settle into the rest of the water and get mixed in there. And it'll every so often is going to check, is it above or at least at 7 gallons, like 7.5 gallons roughly. If not, it's going to keep doing this until it actually finally fills up with water. And then once it actually is at the right water amount, it's going to stop that impeller right there. It's going to stop pumping in water because we don't want any more water. It's going to set this one off. It's going to reset the fill LED because now we're no longer in fill. And also, it's going to reset this machine's switch. So now this machine is no longer connected because we don't want it doing anything after it accomplished what it needed to. So now we're here. We begin automatic. If this is on, that means that everything prior to it has already been accomplished. We're already washing, so we're good to go. So it's going to turn on power to a timer. And that timer will be pretty much counting off until 20 minutes is hit. I thought that sounded like a good amount of time for the clothes to get agitated and washed. It's going to every so often pulse some jets that are located in the impellers to kind of get the clothes moving around more. And then also our impellers are going to move 180 degrees one way, back, and then 180 degrees the other way. And this is going to keep our clothes kind of brushing into each other, which helps encourage them, to get clean. It helps get all the, hopefully, particles like just off of them. And then obviously the LED saying that we're in the wash state will be on. This will keep going on until our timer finally says, hey, it's good to move on. But until then, it's just going to keep repeating. But in the event that our timer says, hey, we're ready to go on to the next state, it'll go on. It's going to reset this timer because we're going to be using this later, at some point later. And then also it's going to reset the LED that we used here and set the rinse LED saying, hey, we're in the next cycle now. So in this cycle is going to start draining the water because obviously this water is pretty filthy now, and hopefully we just don't want it anymore. So it's going to keep doing this until it's finally all gone. After which point, again, this is dependent on what the user said before, is going to sort of repeat what our fill cycle did, except this time it's just going to be plain old hot water. It'll keep doing this until it's finally full, and then go on to our spin cycle. It's going to turn off our rinse LED and then also set the spin LED. And then depending on what the user said before, is going to start our spin cycle. So in this case, we'll go spin pass. At this point, is going to just keep spinning the tub very, very rapidly to encourage the water to, go towards the outside. Our timer is going to be on for 20 minutes. And while this is going on, our drain pump will be engaged so that it's spinning the clothes rapidly. It's draining out all the water. And then hopefully by the end of this time, your clothes will no longer be wet. and they'll also be quite clean. And then at the end of that, once the timer indicates, it's time to stop doing this, it'll reset the spin LED. It'll release the lock so you could get your clothes. It's going to turn off this machine, but also is going to set the finished LED and just play a little chime or buzzer or some sort 3 times. So I chose to segment cycles just because if I did this all in one cycle, the amount of inputs and outputs per one cycle would be very, very hard to manage all at once. And in addition to that, it makes it sort of more flexible because if there is a better way that I say, hey, there's a better way to do this cycle or that part, then you could change it without necessarily changing everything else, so that you could just change that specific part if you want to. This is kind of like the overall black box. The only user inputs we care about are the water temperature, the spin speed, and the amount. And then also that'll say, hey, whether or not you want to go with these choices. And then we got our little clock right there. We got all of our LEDs coming out. All this would be internal because this is all the parts that are going to be automated by the machine, because after this part, our users shouldn't have to care about what else the washing machine is doing. So as an example of what I meant, this right here is a little voltage switch. This right here would be S1, and this would just be controlling whether or not our next machine will be going on. As for instance, right here, you could see right now there's no clock going to it, but then the moment that's set high, hey, now that machine is on and it's able to actually do what we want it to do. And then this is just the same sort of thing, except this would prevent the user from messing around with their choices made after that point. Because in the event where the user just, or maybe their kid comes along and the kid just starts pressing random buttons and they start changing everything, they're going to be pretty upset if hot water is used when they wanted cold water, or if there's too much water used. And right here is my timer. I chose to use a 4060 because the 555 over long periods of time becomes pretty inaccurate, primarily due to the capacitor. So the 4060, as we know, you're able to basically have it so that each individual pin is putting out different amounts of times. It's based off of a table, but for my instance, I knew I just wanted a pin that would be a very long period. So I did some of the math on it. We know that we want 20 minutes worth. We know that in this case, I just arbitrarily chose pin 9. And just that gives us a frequency of so and so. I arbitrarily again let the capacitor in this case just be a 0.22. And after that, you just get an R1 of 780K. And then after this, it'll output right here, it'll be high. And it'll be for 20 minutes, but since the moment the machine detects that it's high, it's going to turn it off anyways. It doesn't really matter. This was my table just for the selector cycle after everything was done. There's quite a lot of present states. All that really matters is these little inputs right here. And then, they input depending on what you chose right here, the different LEDs. We got the same thing for the fill cycle and then the same thing for the rinse cycle. This was the Carnot map just for the next star, or just for the next state for A for the selector cycle. These are just some examples of the Carnot maps that would be produced as I'm simplifying. So after I simplified everything, I decided to see what might work. I was looking at just the basic chips like and, or not. I decided that they wouldn't really be a good value proposition, even if they are pretty low on an individual gate basis. And also, after looking over all the different SOP like equations that I had at the end of this, I seen that there'd be a large amount of gates, so the footprint would be very large, which since this would be going into relatively small console just for the washing machine. You don't want it to take up too much space. So for instance, this right here is for my selector. You could see right here, we have a lot of ors and a lot of ands. And in the next picture, I'm going to show you just like an implementation for just the B star. Oh, and altogether, this is how many ands and ors it would take using up to quad ands and quad ors. This is just for the B, which, as you could see, would take quite a lot of gates. And to be fair, this isn't as simplified as it could be because, again, this is only using 2 input and OR gates. But even using the other ones, once you take into consideration how many that we need, it's just far too many. Also, in addition, the price, even though the per unit price is really, really low, we have, right here, the quad. This isn't in bulk. This right here for under 9 would be only 49 cents a chip. But altogether, it would be $74 for all of our gates, including our flip-flops, because we need some way to keep track of where we're at. So this rough estimate was done mainly by looking up the boards that would typically be going into the washing machine console. No manufacturer obviously does it using gates. A lot of them are, already printed onto there. A lot of them do use non PCB related things, but looking at the size of every gate, like just the length is 8.7. It would take up an area per gate of 53 millimeters squared, which, since I have quite a lot of them, would be quite a lot of space. The flip-flops are honestly going to take up the most, even if they're quad D flip-flops. Those are going to take up a total of like 2,600 of my total area. Altogether, that would be like 5,900 millimeters squared, which is way more space than would be available on my board. So I decided, what about multiplexers? Because multiplexers are, as we learned, they're pretty neat. They're pretty flexible. Just the multiplexers alone would be around $36 total. The operation temperatures would be pretty good. I mean, it's just going to be inside of a console, so it's not like I'm expecting extreme temperature in either direction. The supply voltage, it works with a very large range of voltages, and the propagation delay in this case doesn't really matter, since I mentioned before my clock is pretty slow, but regardless, the propagation delay, at least at 4.5 volts, would be very, very small. So this made me decide I'm not going with muxes, because for everything, keeping track of every single state would be incredibly difficult with muxes. They are more flexible than gates because it's easier to change anything around. But if a mistake were made somewhere in like any of the 43 that I need to keep track of, it'd just be a disaster. And compared to the other choices, especially compared to PLDs, they're just not favorable. In addition, let me move this real fast. In addition, with the flip-flops, they take up quite a lot of space. It's not necessarily the multiplexer's fault. The flip-flops alone are always going to take up around 2,600 millimeters squared of my total space. But with the flip-flops, it's going to be $35 extra, which means the flip-flop multiplexer combo is going to be around $70, which is only $5 cheaper than our gates. So it turns out multiplexers are also not the way I want to go. That leaves us with some other choices, primarily PLDs. I'm thinking simple PLDs because I don't see a reason to get into the more complex ones, which would mean either, ROM or PLA. And then also we could use an FPGA, but it might be cost prohibitive. And also, since the memory is volatile, we need to pair it with some sort of memory storage device, which I don't want to deal with in this case, especially since our design is relatively simple. With ROM, there are a lot of min-terms involved, primarily because of all the inputs. Like this is towards the last part, the last cycle that I shown, which is our wash, rinse, and spin. The amount of min-terms that would be unused would be pretty wasteful, and we don't really want that for ROM. In addition, we need to dedicate more space to the flip-flops, but this is true for anything that would be non-registered. So I just decided I'm not going with ROM on this case. The FPGAs, even the cheapest FPGAs around $8, could give you around 144 inputs and outputs and roughly 1,500 logic gate equivalent. I decided, again, my machine is not that complex. It's a pretty simple machine. It's essentially just going to be deciding, hey, do you want hot water? Do you want a fast spin speed? Do you want a large amount of water? So I don't need the complexity or necessarily even the flexibility that an FPGA would offer us. In addition, as said before, the configuration is volatile. So while our machine is going to be powered pretty much all the time, it's not like somebody's just disconnecting and reconnecting our washing machine. We need to pair it with data storage, and I just didn't think that was necessary. What about PAL? It offers pretty good operation temperatures, especially considering what it's seeing in a washing machine, which is no extremes. It's going to be pretty safely in a console. It works with very thin. In this case, this one works with a very small range of voltages, but that shouldn't really be a problem either. The input to output propagation delay is pretty small, especially in comparison to our clock. And they retain data for a very large amount of time. Roughly 20 years for this one is what the manufacturer was saying. In this case, I don't really see our washing machine. Hopefully, I mean, I guess a washing machine should last very long, but 20 years is pretty good, especially if at the very end, if they want to keep on using that washing machine for a very long period of time, and if it's still supported, they could just get another board. The simplification took quite a bit. But thankfully I already had everything simplified. So let me just zoom in a bit. So we have all of our next states, we have all of our inputs. By this point, it was pretty easy. You know, it's just a bunch of combination. We get our selector, our A star, B star, C star, W, F, H, X, C, Y. And then this is pretty much just repeated with all of our cycles. We have our fill cycle, and then afterwards we have our, this one took the most amount of time. These weren't complex, so to speak. It just had more of them. So that's about the only reason it took more time. There's, as you could see, a lot of them aren't fused, especially towards these ones right here. For my final design, based off of everything, I decided to go with PAL, more specifically the ATF22LV10. They have the 16LV8, which by this time is pretty outdated. There's not really a need for it. The price per gate is much higher than all of our other gates, but since we're using a very low quantity of them, it doesn't really matter that much. In fact, the whole design in total would just be at least for the logic portion of it, $13 altogether. In addition, they take up a very, very small amount of space, which I think is very beneficial. This is using the thin shrink small outline packages, which for all of them, I was using the small outline. So it's not like the other ones were using just the regular ICs that you might see in class, and then these ones were different to skew the results. Altogether, I thought that space is my most important criteria because this is going to be going into a predetermined space. How flexible they are is pretty important, especially since you don't want your washing machine acting erratically. And the more flexible the design process is, the easier it is to make changes if something goes wrong or if you find a better way to do it. And then obviously price, honestly, I think was kind of tied with flexibility. Space is number one. These two are probably close second and third. The PAL would also save us space on the D flip-flops since they're going to be registered output, so we don't got to worry about our flip-flops. It'd be the same sort of thing with FPGA, but I didn't want to worry about the fact that you got to pair that with memory. And that's my final design. Any questions?
Well, thank you very much, Israel. Yes, I have a couple of questions, but
Cool.
Is there any other questions from the panel? Okay. Can I ask you to put your ASM chart back on, please?
Yes. There we go.
Thank you very much. I'm not sure if I missed out or I didn't see anywhere where you added detergent.
Oh no. Okay, so for here, yeah, I'm sorry. The detergent in a washing machine, this isn't going to detect whether or not you use detergent, because especially some people, you don't really need detergent, I'd say, in some cases. Like, if, say, you're a student and you're just going to class, your clothes, just to the agitation of hot water added, would be enough to clean your clothes. The detergent is, I hope I'm getting this right. It works the same way as, say, soap does, where it'll help the water actually dig into the dirt, but you don't necessarily need it in a lot of cases. The detergent would just be an external little, like a container, so to speak, added, and water would flood into that detergent and then into our tub. It doesn't care whether detergent's actually added or not. That's not really part of our machine, so to speak. It's just gonna flood water in there regardless of whether or not you actually have detergent, if you get what I mean.
I do. I'm just looking at it in terms of you've taken this design to a very reputable, famous manufacturer and you want to sell your design. That would be because, well, you have to add some kind of
Sensor?
soap or powder, or I mean, I call it detergent, anything
Yeah.
that you add in order to not only clean, preserve your clothes. So that really needs to be added, and you would expect that if it's not added, the machine would remind you.
Okay.
Yeah. So that would be something that we have to include. Whether you do it or not, I mean, you could just press a button as if you have, but at least that option has to be there.
Okay.
Okay, so that's the first question. Now, please, if others have questions, you can interrupt me. I have several questions that I would like to ask, but everybody else has the right to ask questions. I remember you saying at the very beginning that you chose your clock to be very slow. I'm not sure why you want to do that.
Yes. Roughly 5-second period.
Why is that?
I just thought that it'd be the simplest way, because we know that immediately it'll go from that state to that state. So I chose the clock to be very slow, just to give the user, especially because I had different designs for the selector in specific. This one I redid a lot, but using this design, I wanted to give the user period of time, so to speak, to choose which one they wanted to do, because by default everything will be low in this case, at least.
Right. Yeah, I can see how your mind works, and I honestly would like that very much. But let me, I mean, again, I'm looking at it in terms of someone else. So is 5 seconds long enough then?
It may not be, actually. It might be too fast for the user. But in that case, and unfortunately, especially based off the way it's designed, there's no like it it'd be a very sloppy fix, but they could power cycle it. But if not, they they always have the option to choose whether or not they want to confirm those choices, and if not, they will be reset. So hopefully by the second time around, they'll know what they want. And if not, they could just keep waiting until they actually want to get the washing machine going. So
Right. Yeah, I guess you're right. Yeah. You see, also let me also make sure that you understand the reason I ask these questions and I bring these points, because I love this design, and I honestly think that this is sellable. This is presentable. You can actually offer it to manufacturer, because there are several advantage of this design in terms of those who are environmental conscious people, as how much water they want to use, what temperature they want to use. See, these are people who would prefer if they have the choice, if they can control their life. So this has at least got this very important aspect in your design. But it can easily be modified if, for example, this 5 second, as you just explained, if this 5 second is not long enough, you can easily modify that. It can be there. And I like very much your final choice as PAL. I think you perhaps meant to say, and you might have forgotten to say, that the fact PAL is the only device that is registered output, so you could do without all those flip-flops. That would be yet
yeah,
another.
especially in our case, those would take up quite a lot of space, even the smaller flip flops. So.
Right. So I really approve and like your final choice. Now, so one other minor suggestion that I would make, when these LEDs come on in various states, maybe you
Yes.
want to put those as outputs on a different elliptical shape.
Oh, so more of a melee type thing. Yeah, I was thinking about that. I didn't want to clutter everything too much because that was my first design. My first design was giant and very, very difficult to see what was going on.
Right.
This right here was the third time after I deleted everything and then started up from the ground, because I'm like, it's got to be readable, especially once you're trying to put it into a table, or else you're not going to know what's going on when you're trying to simplify everything. So, but yeah, those should be
Yeah.
it'd be better if those were melee.
I mean, for who, because I mean, by default, you are the one who would program the PAL, and you're the one that would give the PAL to the manufacturer and say, here it is, use it. I mean, that PAL would be your entire design that you need. I mean, that's all. The only thing that would be left is the wire. So yes, I mean, so the chart is really not part of what you need to give, but if you do, at least it would be more understandable for whoever wants to reprogram in future and whatever, or modify or whatever.
Yeah, I was sort of thinking of more of a, like you were saying right there, a maintainability sort of thing, especially if, like, say you were working with others on this and you want to make it legible for them. Like, say in coding, you add comments both for yourself and for others so that they know what this is doing if it's not able to explain itself in the code. And even then, sometimes if it explains itself, you'll probably add the comments anyways, just so that they're like, oh, for sure, that's what he was going for there, not like maybe they're trying to guess what you're trying to do there. So
exactly. Okay, now let me give you the how I took this designing. Firstly, you look very smart. Thank you. Secondly, you were so confident in describing your design, and you're so clear and confident, and you knew exactly what you were saying, and you were passionate about your choice. So in all, if I was to make the final comment, is please go back and add that detergent somewhere. And then this is, to me, a very complete design. I don't at this moment see anything wrong with it, but when I see your report, I might even, I don't know, as I say, I don't know. I will be scrutinizing in more great detail. So at the moment, I don't see anything wrong with it. I think this is great. You've done a very good job.
Thank you.
I thank you very much, and you're exempt from the final exam.
Thank you.
Thank you. Super.